Hello, everyone. It's a pleasure to have Michael Dibaee as our special guest today. He's CCNA certified and will be sharing his expert insight on layer 2 concept and troubleshooting. Without further, I'll pass the floor to Michael, and he's going to talk about this topic. Michael?
Hello, everyone. My name is Michael, and Hamid already did the introduction, so no need from me. Today, we're going to work on layer 2 concept and troubleshooting for getting ready to answer some like weird question they might ask you on the interviews. Like they're simple question, but important enough to any troubleshooting process on any networking job that that in, that has that needs you to do it. Okay, so I'm just gonna share the scenario that I created on the GNS3. So to make everything a little bit more understandable, and we have a context here so we can talk about it on that instead of abstract, paint pictures. Okay, we have this scenario here. We got two switches. There is a trunk between these two switches. We got we got different VLANs. The green, the green are VLAN ones, the yellow are VLAN twos, and the blue is VLAN 99. So by looking at this topology, you might just look at it and say, "Oh, that is wrong. This is wrong. Why is it like that?" So that's the purpose of it. We are here to talk about the concepts and why this is wrong and how can we fix it and how we can troubleshoot. So for starters, we're gonna start from a simple concepts. So these concepts are basically kind of based on, so we have a context about the questions. PC1 is part of VLAN 1, PC2 is part of VLAN 2, PC3 is part of VLAN 1, and PC4 is part of VLAN 2, and router is part of VLAN 99. And the NAT cloud here represents internet. And on R1, we have routing setup, so it can access the internet. We got all the PCs are here. They're set up with a static IPs, no DHCP, and we're gonna talk about DHCP later on, so don't worry about it. So right now I'm gonna ask Hamid to ask me the questions.
So one of the things that I'm thinking about PC1 and PC2. So how's going to be the ping process between the PC1 and PC2?
Okay, so when PC1 is trying to ping PC2, it's trying to ping the IP address of PC2. So like it looks at the IP that it's trying to ping. It says it's on the same subnet as itself. So when a IP is on the same subnet as the PC itself, PC1 look at it as at its ARP table and see if it's already have a MAC address entry for 10.0.0.2 to send the packet out. But since this is the first ping, it doesn't have it. So it has to ask where is PC2. So it sends the ARP request out as a form of broadcast. So the destination MAC of the packet is gonna be FFFFFF. So like it's better to like draw it out. So PC1 is trying to look for the where PC2 is. So it sends a F broadcast MAC. It goes to switch. The switch receives when a switch receives a broadcast packet, it will forward it out of every port except the port that is received from on a same LAN segment. And that when the difference is here, the difference between VLANs are here. So we have set up VLAN 1 and VLAN 2 on these two ports. VLAN is basically virtual LAN. It's basically taking a LAN and you're segmenting it logically. So the switch, when it tries to forward that broadcast packet, it will forward it back only to the ports that are connected to VLAN 1, not any other VLANs. Therefore, it cannot forward the ARP request back here. Therefore, PC2 cannot answer the ARP request. Therefore, the PC1 is not going to have a destination MAC for PC2. Therefore, it cannot ping. The destination is unreachable because there is no resolve. Like PC1 cannot resolve the MAC of which the packet is going to be sent. Therefore, no packet is going to be sent. And that's going to be the answer for that question.
Okay, so let's say now PC1 and PC2 are in the same VLAN. So now how switch forward the packet between the PC1 and PC2 when they are in the same VLAN?
When they're in the same VLAN is basically, as I explained before, so the ARP request goes out, switch receives the ARP request, switch records the MAC of PC1, let's say MAC of A, as port gig00, and then it forwards the broadcast traffic to all ports except the one received on the same VLAN. Therefore, the ARP request is going to be sent to PC2. PC2 is going to receive the ARP request, is going to answer to the ARP request saying that I'm PC2 with its MAC. Let's assume the MAC is B. Is going to say I'm PC2 is going to say I'm MAC B with the address of 10.0.0.2. That's going to be the ARP response. And the ARP response is going to go back to the switch with the destination MAC of PC1. Because the packet sent to PC2 already has a source MAC of PCA. So PC2 knows where the packet is sourced from. So the PC2 is going to send the unicast packet with its own source MAC and the destination MAC of PC1 with saying that I'm MAC address B with address 10.0.0.2. The packet is going to hit the switch. Switch is going to see the destination MAC being PC1, and the switch is going to forward that packet to the exact port of gig10 because switch has the CAM table. The CAM table for the switch is basically a table that the switch associates as a port to a MAC address, not an IP to a MAC address. This is not an ARP table, it's a CAM table. So switch is going to look at it, it's going to say, okay, MAC address A is on gig10, so I'm going to forward all the traffic destined for MAC address A through gig10. And PC1 is going to receive the ARP response, is going to add it to its ARP table, and therefore it cannot now create a packet with the destination address of PC2 and a destination MAC of PC2, and it's going to forward that ping packet or ICMP request to the switch, and the switch having both MAC addresses right now can forward the packets, and PCs knowing each other can encapsulate can create the packets to respond to each other. So now you have a full session at this point. I think that's everything about it.
Okay, so I assume that we're gonna discuss more in troubleshooting. You show us the CAM table when we are troubleshooting every switches and every PCs. So the next question is going to be like this. Okay, let's say PC1 wants to reach to the internet. So how's going to be the packet process and how we can reach to the internet from PC1?
So PC1 is trying to reach the internet. Like if we do not consider DNS resolving, let's say PC1 is just trying to ping. It's trying to ping 888. There is no DNS name resolution here at all. We're just trying to ping internet, right? So PC1 looks at the destination address of the packet of the ping. It's gonna say, okay, we are trying to reach to an address that is not locally attached. So PC1 at this point, it doesn't know where to send it. So if not configured with a default gateway, PC1 cannot ask. PC1 doesn't have anywhere to send it. So the address is not resolved. The host is unreachable. So what PC1 is going to do if a default gateway is set, is going to send that packet to the default gateway, assuming everything here is configured correctly, which is not. Is going to PC1, since it is already configured with default gateway, is going to send the packet to its default gateway for the ping 888. It's going to say, okay, that's my default gateway. If I do not know where a network is, I'm going to send the packet to my default gateway, and the default gateway can deal with the packet. So the way it works is that the resolution for accessing the router is the same as resolution for accessing any other network on the same subnet. So it's going to send a broadcast MAC ARP request. The router is going to respond to the ARP saying where it is. And the moment PC1 can produce the packet with the right source destination and destination MAC and source and destination IP, the packet will hit the router interface. the router, okay, looks at it. Router says, okay, I have a packet with a destination IP of 888. The router at this point either has the route for 888 or has a default route saying where basically forwarding a packet to another router, which is supposed to be here. So at this point, our router doesn't know about 80. It doesn't know where 8888 is, but it has an entry in its routing table of where 888 might be. So it's gonna send the packet this way. Since the router does not know where 888 is, it needs another protocol here to translate the IPs, because if a packet is going out, it should come back in a matter if we are pinging. So we should have something called NAT, network address translation, set up here. So when a packet is sent out using a default gateway, the router on the internet knows how to get back. So the router on the internet doesn't know where your PC1 is, but it knows where your R1 is. So so you would set up a NAT on R1 gig 10. So when the packet for 888 goes out and it's trying to come back, the NAT, which stands for network address translation, translate the IP of R1 gig 10 to the IP of PC1 IP. That's the basic of a NAT. You just translate an IP to another IP. We got 3 different types of NATs we can use. We can use a dynamic NAT, which is a pool of IP addresses assigned based on how many. It's a pool based on requests, basically. So I have, let's say, 3 public IPs. I got 5 private IPs, and there's only 3 public IPs available for 3 private IPs. It's gonna like dynamically assign. Or we can have a static NAT. Basically, okay, we're saying that any packet for 888 goes to PC1 10.0.0.1.1, 10.0.0.1. Or we can have PAD, which is port address translation. It's basically you are translating a private IP to a port on a public IP kind of thing. So at this point, it does know how to get back. So the router on the internet forwards the 888. 888 is coming back. It hits our PAD. Okay, PAD looks at its PAD table. Okay, it says that okay, PC1 10.0.0.1 on this port is gonna forward it back to the PC1. So over all of this, you're gonna have a very weird, very badly drawn session set up through the default gateway address, default gateway, the NAT, the routing. Basically, it takes this much to make everything work. And like if the ping doesn't go out, the problem can be within any of these layers. But that's a concept for our troubleshooting section.
Okay, great explanation about this concept. So now let's talk about PC1 and PC3. So they are in the same VLAN, but they're connected through the trunk. Let's say you want to contact with the PC3 from PC1. So how's going to be the process, like the topology and the packet process between PC1 and PC3?
Okay, so the concept of VLANing is per switch. So like the VLANs, although the naming and the numbering system for the VLANs are the same, you cannot have a switch link, which is basically a VLAN link, to talk to other VLANs, because it's not a transitive concept if not configured so. So on a switch device, there are 2 different links. You got access links and you got trunk links. Access links are basic switch ports that we usually use with mostly dumb switches that are not configurable. Access ports are assigned to a VLAN, to a LAN segment. They can only forward a packet for one LAN segment because that's how they're configured. trunk ports are configured to carry multiple LAN segments over the course of the network. Like what the reason we need trunk switches, trunk port, is basically we cannot have a big switch that we connect all our devices across multiple platforms to keep our VLANing systems. We cannot rely on one switch across multiple sites. We need different switches with the same VLANing scheme to segment our network access. So we would use trunk over this link here to to translate the VLANing between these switches. And the way it does it is use the .1q. It uses a .1q protocol to basically tag the packets as they go through this trunk. It tags the VLAN ID. It tags the VLAN ID over the package that is distinct to another VLAN, or the same VLAN. It only doesn't tag it if it's a native VLAN, but that's another topic for a different question. But let's say if PC1 is trying to contact PC3, right? And basically it sends its broadcast. It knows the IP because we gave it. It basically it sends the ARP request out for VLAN 1, right? It sends the ARP request out, and the switch one looks at the ARP request and looks at it. Okay, I cannot send it off gig 20 because it's different VLAN. I cannot send it over gig 10 because it's its own. It's the source of the broadcast. It cannot do it over gig 33, but it can forward the packet over the .1q trunk because that's the only way it can send it out. It sends the ARP request with the ARP broadcast request and tag it with VLAN ID number 1. And switch 2 receives the broadcast traffic. It de-encapsulates the .1q VLAN ID and reads it. Okay, there is a broadcast traffic from this trunk link destined for VLAN 1. Then it looks at its VLANs and it says, okay, I got a gig 10 for VLAN 1. It de-encapsulates the package and forwards it to the access ports of gig 10. The PC3 responds to the ARP request the same way. This time is a unicast packet, but it's the same concept really, because switch 2 is trying to forward that unicast packet back to switch 1, and it doesn't have a direct access to it, but it has a trunk link. It tags it with VLAN ID 1, and switch 1 receives it, sees the tag ID, says, okay, this packet is for VLAN 1. It forwards it into VLAN 1, and now they can form a session because the switches can basically talk to each other about the VLANs they have. If PC2 were to contact PC4, same concept. It would tag it this time with VLAN ID 2. And now you can have a fully segmented network the way you want it, and it can hop over multiple switches and no problem.
So that's great. So that means that switches every time use the tag to talk each other, and they check the tag when, for example, one PC is sending out the packet to other PCs.
Yes.
So let's talk about now the vulnerability on layer 2 switches. Let's say that we want to find the vulnerability about these switches. Let's talk about the vulnerability that we have on layer 2 switches, how like flooding the switch. So let's talk about this kind of stuff.
Okay. Between two switches that have the capability of forwarding broadcast traffic, there is a vulnerability. So if I have a switch here and another switch here, and there is two ports connected to each other like that, it's the same situation we have here. If a broadcast packet is generated through this link, this switch A, switch B, switch A, okay, switch B receives the broadcast traffic, and it is supposed to forward it out of every port except the received port. So it will forward traffic back out of the upper link. So switch A receives the broadcast, and it's supposed to forward it out of every link except the incoming link. So if we forward it back out of a down port, it forward, same thing. It goes on. So now you have a loop. So this loop will flood your network so much that the switches CPU and RAM will heat up so much that basically just turn down. Your switches will turn down, your network will just turn down, it all crashes.
So how we can do a loop prevention here?
Okay, so switches have a method. They use a protocol called STP, or a spanning tree protocol, to basically prevent loop. When having a spanning tree protocol, a very basic example of a spanning tree protocol is that we got three switches connected to each other like that. So in this topology that I just drew, we got A, B, and C. In this topology, we got a loop, because if a broadcast goes out, it comes back in, it comes back in. So what STP does is STP uses its own BPDUs. It basically tries to eliminate the point of loop the best way possible. So the way you would prevent loop on this topology is basically by putting one of these links as down. And that's how we would fix it manually, but STP does this dynamically. So STP chooses let's say a root bridge in your whole LAN segment. STP chooses a root bridge. For example, this time the root bridge is going to be PCB. If switch B is the root bridge, then these are designated ports. All the switch ports on a root bridge are designated ports by default. The switches directly connect to the root bridge have root ports. Root ports. What? Has root ports. So both designated ports and root ports that are between the switches to the root bridge are in the forwarding state. So these links are fully operational. But the link between PCA and PC3 here is that they have to talk about which one of them becomes another designated port, and which of them becomes the blocking port. And whether which of these two ports becomes a blocking port, it will bring the whole link down, therefore preventing the loop. The important thing about STP is to remember that STP works on a LAN segment basis. So it works on your access switches, access ports per VLAN, and it works on your trunk links based on the way you configured your trunk links. So like if you have two switches connected to each other and they're part of the same VLAN, and that you don't configure the links between them, like this scenario here, as if you don't configure these as trunks, you're still gonna have a CP working on that LAN segment. But if they were trunks, it would not care about the LAN segment. You can have multiple VLANs here, multiple VLANs here, multiple VLANs here, and you will still have a STP working on these trunk links basically disregarding of the VLAN configuration. That's the basic of the very basic of STP. Later on, there were other protocols added, other functions added on top of STP that made it work per VLAN. So like that's another concept, but you can have multiple VLANs. You can have a looping topology. I can use all these three links forwarding, but for different VLANs. Now that's another that's a very complicated concept on itself and not really applicable here. But here, basically, the way STP works is because we have two trunk links here. We haven't set up port aggregation yet, so we have two trunk links. The STP is basically going to block either the upper port or the downer port based on how it chooses. So there is no way for a loop.
So let's now talk about port aggregation between two switches. Let's talk about some stuff like how these two switches understand each other, how's going to be the network performance between two switches, and talk a little bit about the speed here, like how's going to be the speed when you bundle, for example, two ports together, okay?
First of all, we have to look about why do we even need port aggregation in a scenario like this. So the reason we need port aggregation and we should do port aggregation is based on the concept of STP itself. If I'm connecting switch 1 and switch 2 together and configure these two as trunk ports, right? As we discussed, one of these ports is not going to be forwarding any traffic at all because STP blocks it. But the reason we are using two ports is we want to have more bandwidth. We want to have more throughput. We're going to use all these two links. So the concept of port aggregation comes when you basically bundling multiple ports as one logical port, so we can use all the bandwidth and the throughput the links gave us. And when they are considered as one logical port, the STP is the switch and the STP is going to look at it as one port. So when the broadcast traffic goes out of one port channel, and the other switch receives the broadcast traffic, is not going to forward the broadcast traffic back to the same port channel because it looks at it as one logical link. And basically, to achieve this, to achieve having port channel and switch 1 and switch 2 know about each other port channel, we got port aggregation protocols or link aggregation protocols. We got PACP and LACP. PACP is Cisco proprietary, LACP is industry standard. So basically, the way they work is they send like health check packets between the links to let the other switch knows that there is a port channel over there, and the switch itself lets another switch knows there is a port channel here. So the switch can establish the logical link the way that it is intended to be. So it works as a single link if they can communicate. There is a static aggregation that you can do. You're telling the switch that this is a port channel. I don't care about the other switch. And you tell the other switch, I don't care, this is a port channel, but I know this is a port channel, you don't care the other one. The downside of that is if the port channel goes on one switch, the other switch has no idea. And then you can have a loop. Then the STP is not going to work the way it's going to work, and your network is going to be broken. So it is recommended to use port aggregation protocols because if one link goes down, the another switch knows the other link goes down. If this link goes down, that link goes down. So you got a full, basically you have a full connectivity and you can use the full bandwidth and full throughput of the two links that you're deciding to use. And the way this affects the performance of a network is the reason you do it, because you can bundle link speeds on top of each other to have more speed and more bandwidth between your networks. But it's not as simple as it sounds, because when the switch is deciding to forward the packet, it has to still choose between which of these two links to send it out to. Then the switch has the method called load balancing of the port channel, which is based on attributes configured by the switch that it chooses which port, which of these two links that I have, I'm gonna send out the packet to. Is it this one or is it this one? Which one I'm gonna send? And no, it doesn't do it by random. It doesn't do it like one this, one that. It has attributes like source MAC, destination MAC, source MAC, destination MAC, source port, destination port, source IP, and destination IP, which is totally customizable based on the engineer need. And based on these attributes, the switch is going to calculate the hash. And based on that hash, then it decides, okay, if this hash goes to this link, this hash will go to this link always. If this hash goes to downlink, this hash uses the downlink always. So based on this concept, it's gonna be a little bit tricky. Are you actually using the full bandwidth or not? Because the default attribute for the switch is to calculate based on the source MAC. So if PC1 is trying to contact PC3, switch 1 is gonna calculate the hash based on the source MAC of PC1. And if it decides to send it on gig 01, it's always gonna use gig 01 to forward packets for PC1. And switch 2 receives it, and because switch 2 receives it over the upper link, switch 2 is gonna send it back to the upper link. So if the speed of both of this link is gig. When we bundle them together and we are expecting a speed of 2 gigs, but it's not because of the attribute of the load balancing of the switch, you're not gonna have the full 2 gig speed over a single session between PC1 and PC3. You're still having a maximum speed of 1 gig. But if you have, let's say, other attributes set, you can if you have other attributes set, you can manipulate the switch load balancing in a way so it can form multiple sessions over multiple links. Then you can utilize the full 2 gig speed. Otherwise, you can't. I think you can utilize you can use the best one is source IP and destination MAC, I guess. Like there's I'm not sure on that, but there are multiple load balancing methods you can use to maximize the speed of a connectivity with 2 nodes. But that's not this is the way you can like optimize the port channel, but this is not really the reason you do the port channel. The reason you do the port channel is basically to increase the bandwidth, not for a single connectivity, but for multiple connections from multiple devices to multiple devices. Because that way there are different hashes calculated, and they can choose either the top one or the bottom one. This one choose the bottom one, that one choose the top one. And this way you can utilize the full bandwidth for different devices, not for 2 devices on a single session. I think that is all I can explain about the port aggregation.
Thank you. Perfect. Yeah. So let's clean everything and now talk about DHCP on router 1. So I am assuming that, let's say that we have configured DHCP on router 1, and PC1 on VLAN 1 wants to receive an IP address from DHCP. So let's talk about the process, how it's going to be the sending packet, requesting packet, and asking DHCP server to assign an IP address to PC1.
Okay, if PC1 is the only one asking for a DHCP in this question, we have to assume first everything is configured correctly. So the switch will forward the broadcast traffic out of gig 33 out of gig 33. Assuming if all is good and switch 1 can do that, it's the same. The process is PC1 is configured to receive a DCP address. Therefore, PC1 based on PC1 for generates a broadcast DHCP discover out of its own port, asking for an IP from any DHCP server. PC1 is not configured to ask from a specific DHCP server. Therefore, it sends out a broadcast packet asking where is DHCP. Switch 1 is going to forward the broadcast traffic to R1, which is configured with our DHCP server. R1 is gonna receive the broadcast packet and is gonna generate an offer to the PC1. This is a unicast packet, not a broadcast packet anymore, because R1, the DHCP server, knows about the client. So there is no need for it to be broadcast again. So R1 generates a DHCP offer with the destination MAC of PC1 and sends it to PC1. PC1 is gonna receive an offer, and based on if he likes the offer and he can accept the offer, is gonna generate a unicast request, DHCP request to R1 saying, yes, I want this IP. And R1 is gonna receive the request and it's gonna send a unicast ACK saying, okay, you can have this IP, and R1 is gonna locate, DHCP is gonna locate one of its pool addresses to PC1, and PC1 is gonna receive that IP. It's gonna basically configure that IP based on the offer that it received from the DHCP, which is basically the subnet. The offer is gonna give the PC1 a subnet, a network ID, and an IP from a selected pool, and based on a DHCP option configured, it can give the PC1 a default gateway, a DNS server. It can do all of that. But that is the way basically DHCP DORA, or discover, offer, request, ACK, works for a client to receive an IP from a DHCP pool.
Great. So we reached to troubleshooting section. Basically, in this section, I'm gonna ask you like some scenarios, like why there is some issues in the network and we want to fix the issue, and you give some suggestion how to fix the issue. For example, let's say PCs are trying to get to the internet, but there is no result. So what are the options, the first option that you check to reach to the internet?
Okay, if I am a client on PC1 and I'm troubleshooting from the perspective of PC1, first thing I should do if I cannot access the internet is start from my own computer for troubleshooting. So first thing I have to check is the Ethernet link is even connected in? Do I even have connectivity to the switch that I'm connected to? If so, do I have an IP? I have an IP. Do I have a correct default gateway? That should I check. If I have the correct default gateway, like first of all, when I say correct default gateway, if I'm on PC1 and checking my default gateway, it should be on the same subnet as the IP I'm given. If I have a default gateway on a different subnet, that's a wrong default gateway. Second of all is I have to check the connectivity to what I call default gateway, which is going to be 10.0.0.254. Like if my ping to the internet is not going outside, I have to first check if I can ping my default gateway, because if I cannot ping my default gateway, it means something wrong with the configuration, either on my default gateway, which maybe the default gateway actually there and the switch is configured correctly, but the IP is wrong. That is possible. But that's a layer 3 troubleshooting. But first we have to resolve all the layer 2 troubleshooting issues. So I'm gonna start from looking at the switch that the PC1 is connected to. Okay, let's remote into the switch. I'm just gonna pretend. Can you see the Mobax term? Can't, right? No. No Mobax term. I'll give me.
No.
Right now, it should be there, right?
I can't. Oh yeah, that's there.
There it is. Okay, I'm just gonna assume that I don't see the VLAN 99 being different than VLAN 1 here. This is just for the purpose of the topology being understandable. On an actual troubleshooting environment, you have no idea. You cannot look at a topology and see that's VLAN 99, right? So first of all, I'm gonna make sure that the link to R1 is on, which is gig33 on either on the same VLAN as PC1, or is a trunk link configured to forward the VLAN traffic to R1. So what I do is basically on switch one, I go to show VLAN, right? Then I find it, okay. Yeah, gig33 is part of VLAN 99. Therefore, there is no way my PC1 can contact the default gateway to go to the internet. So I have to fix it. Two ways to fix it. Either I go to interface gig33, in the gig33, and basically switchboard access VLAN 1, right? And if done so, I should be able to ping. We open PC1, and we try to ping our 10.0.0.2.5. Because R1 has IP. You show IP interface. Okay, gig330 is up. Do show VLAN. Gig33 is part of VLAN 1, and gig10 is also part of VLAN 1. So I gotta go onto the router itself and show IP interface brief. It is configured with 10.0.0.254. So it should ping. Yes, I ping.
Of PC.
That's what I'm trying to say. Show IP. Okay, that's our PC doesn't have an IP. That fixes it. IP address 10.0.0.0.1. We are configuring the gateway for. We will be giving subnet of /24 10.0.0.0.254. Valid address. Why?
IP.
There is. And let's see, show IP. Oh, yeah, an IP. Let's ping our default gateway. Oh, we have ping.
Great.
Can we ping the internet? Let's see. We can ping the internet. So that's one way of fixing it for VLAN 1 and VLAN 1 only. You wouldn't fix it like that. You would basically set up a trunk port on switch 1. And configure sub interfaces on R1, like the concept of a router on a stick. So the different VLANs can access the same router for going to the internet. But so we should fix it like that, so our PC2 can access the R1 as well. Because if I go to PC2, right? I don't think there's an IP here. No. And 002 255 And if I try to ping my default gateway, see, no result. The reason is VLAN 2 is not resolvable to VLAN 1. So on switch 1, I should whatever. On switch 1, I should not put gig330 as part of VLAN 1, but I should configure as a trunk port. So interface gig33, switch mode trunk encapsulation .1q, switch port mode trunk, and encapsulation. Okay. When configuring the trunk here, that at first create issues because right now, let's see if we can still ping from PC1. As you can see, the ping is dead. Not only I didn't fix it, I made it worse. Because that doesn't fix it, because R1, when configuring the switch gig33 as a trunk port, switch 1 will target the traffic from VLAN 1 and VLAN 2. And R1, when receives the encapsulated packets with the tag, it doesn't understand it. So there should be something done on R1, right? So you go to conf R1 interface gig00 encapsulation. Nope, doesn't support it. So the way you do this, configure router on a stick, is by creating sub interfaces. So first of all, under the int gig00, I should remove the previous default gateway IP address, because the concept of the sub interfaces does not allow me to use the same subnet for all my VLANs. Because the moment I configure router on a stick, I will allow access from VLAN 1 to VLAN 2. And because there is a sub interface, there should be a sub interface for each VLAN. And each of the sub interfaces has to have an IP. I cannot use the same IP for multiple sub interfaces on the same route. Therefore, we should fix the IP addressing on VLAN 2 and VLAN 1 and VLAN 1 and VLAN 2 as well. To make it a little bit easier, first of all, we have to remove the previous IP address, which we did. Then we have to create the sub interfaces. I create sub interface 1 for VLAN 1, encapsulation .1q, the VLAN ID 1. I give the IP address of 10.0.0, 10.0.1.254, 255, 255, 255, 0. No shut. Exit. And I have to create another sub interface for interface 002 for VLAN 2. Encapsulation .1q 2. And IP address 10.0.2.254.255. No shut. And right now, if I go to PC1, we cannot ping Ethernet. We cannot ping our default gateway because it doesn't exist anymore.
So because your IP address is not in the range of your sub interface, right?
Exactly. So we got to fix IP. 10.0.1.254.255. Oh, sorry. 1.1, 255, 255, 255.0, 10.0.1.254. So now we should have fixed the problem of, yep, the ping is back. So the benefit of doing is that this works for VLAN 2 as well. So if I go to PC2 and I configure the correct IP address, then 0.2.254. Now PC2 is able to ping its own default gateway right now. which it wasn't able to before. And PC2 right now has internet as well. Time up. Yeah. Is a NAT.
Maybe NAT problem.
It's a NAT because the access is on the NAT does not allow it.
Yeah.
So that's a different troubleshooting. But what should happen right now, and it's a little bit weird, is now I indeed from PC2, I should be able to ping PC1. Although on different VLANs, because they're on different subnet, it goes to the router and router forwards the packet back into trunk, and now it can access PC1.
Perfect. So now let's talk about, I assume that you configure DHCP on router 1.
Yes.
So let's now talk about this one, then how we can receive an IP address on PC1 through the DHCP.
Okay. So like since the on R1 is already configured with the DHCP configuration, but if I PC1, I go IP DHCP, let's see what happens. It fails because cannot find a DHCP server because PC1 is on VLAN 1 configured to use sub interface 1 on R1, which has an IP of 10.0.1.254. But the config for our DHCP server was configured for the wrong addressing scheme, which is 10.0.0.0. So the DHCP server being on a different subnet, then it will not respond to the to the DHCP discover on VLAN 1. It just doesn't answer to it. So first of all, we gotta basically fix all of this. So name it IP DHCP pool for VLAN 1. Network 10.0.0. Network 10.0.1.0. And default router 10.0.1.254. And is it. Technically, we should be able to right now receive a DHCP address. Yeah, see, we got two. We have the IP, and we should, of course, should be able to ping our default. Yeah. The goodness of this is I can just create another pool for VLAN 2. Configure this for VLAN 2. And PC2 should receive a DHCP as well. There it is.
So awesome. So now we are in configuration mode. And we can see more in detail, like destination MAC address, some stuff like that. I want to like talk about destination MAC address of the first packet on the network.
As I explained before, the destination MAC of the first packet on the network, because if you're trying to contact something, the most basic connection you can make to a device is by pinging its IP address. And to ping an IP address, that IP address should be resolvable. And what protocol do we use to resolve IP to MAC addresses? Is ARP. Then ARP request has to go out to find a MAC address that is already not on the ARP table. That's a broadcast. That's a broadcast packet, which the destination. To make a broadcast packet, the destination MAC is FFFFFF. It's 8F. Yeah.
Yeah. And can you show us like a was that the MAC address table on switches, like to see that what MAC
So
addresses now
since
we have.
I can do that. Since I already pinged from PC2 to PC1, right? Just for the sake of it, I can do it again, right? Let's ping from PC1 to PC2. Ping 10.02.2, right? Ah, there it is.
Yeah.
Let me avoid it first. So we go to the switch and do show cam table.
MAC address table.
I got this table.
MAC probably is a space address.
There it is. As you can see, we can see the cam table of the switch that was dynamically learned. So through gig10, which is connected to PC1, it learned the MAC of the PC1. When the ARP request came, when the ARP request was generated from PC1, the switch learned this. When the ARP request was, when the ARP response was received from PC2, the switch learned PC2. And the reason you see two different entries for gig3 for the router is basically because of two different responses. That's all. For the sub interfaces. The sub interfaces are two different interfaces, but with the same MAC address. So they respond to the same MAC address. So you can see the cam table, and I think on PC1 we can see the ARP table too. I don't know if the VPCs here supported. Show ARP. Yep. You can see the ARP entry for the default gateway. And the reason you don't see an ARP entry for PC2 is because it's on a different subnet. It doesn't because PC2 is on a different subnet, it doesn't hold the entry in its ARP table for PC2. It only holds the entry in its ARP table for the default gateway because that's how the packet is being routed to PC2. If PC1 is pinging PC2, it goes to R1 and R1 sends it to PC2. That's why there's only one entry on our VLAN 1.
So now let's say source, let's say the packet goes through the internet. What is the source destination MAC address before hitting and after hitting the router, you know?
Okay, since the NAT access list on the R1 is wrong, I'm just gonna fix that. Because if I do show, because technically PC1 is supposed to be able to ping the internet, but it can't. The reason is because for the previous wrongly configured network, we know we can access the default gateway, but the reason the ping doesn't work, it probably is our NAT is not working the way it is. It's supposed to be. So on R1, let's see the access list that allows the IP addresses there. Do show access lists. So standard IP access is 1, permit any. So if this is permit any, why can't I ping?
Check the show run configuration.
Show run section. Oh, the reason is, let's see, do show run and view the context. So interface gig 00 is configured IPNet, but the sub interfaces are not configured as IPNet inside, so there's no translation happen. So I should go interface 600.1 IPNet in interface K00.2 IPNet in exit, and hopefully we got ping here. Yep, ping is back. So just for the purpose of visibility, I'm just gonna make a infinite ping so it doesn't stop. And now we can Wireshark it and see how does it work. So if I Wireshark before it hits the router, basically here, and after hits the router. Just a second, it's kind of gonna be here for a sec. So on the right side, we got before hitting the router. On the left side, we got after going to the internet. So if I just take one of these packages, this is after the router, so I'm just gonna get this and review the Ethernet frame and the IP header. Same thing here. Take one. Take the Ethernet and the IP header. So you can see that the source MAC and the destination MAC before hitting the router, the source MAC is our PC and our destination MAC is our router. But after hitting the router, you can see that the source MAC, oh, this is the wrong packet, my bad. So you gotta find a packet that's sourced from this one here. See, the destination is the router and the source is the PC. And here, if I find the one that the source is the router, not that one, this one, yeah. So this one you can see, this one.
We can stop.
Yeah, good idea. So as you can see, after it hits the router, the source MAC becomes the router, and the destination MAC becomes the NAT cloud or the next hop, basically. As you can see here, the sources are this technical different, and the destinations are different because of the when a packet reaches the router de-encapsulates the header, the router de-encapsulates the packet and encapsulates it again. Because this MAC is interface specific, IPs are translatable over the course of over a layer 3 network. Layer 2, it should be directly connectable. So like the reason the router works like that is if a packet is going to be sent, there should be a source and a des MAC. If the source MAC is not the one that the source MAC has to be the one that's sending the packet out. Destination MAC, it should be the next hop that receives the packet. It's because layer 2 is not expandable over the course of multiple routers. Layer 3 is. That's why a router, when receiving a packet, it de-encapsulates, it removes the layer 2, finds a resolution in its routing table, encapsulates the packet again with the new source and a destination MAC, and sends it out to the next hop. But that's a layer 3 concept, so I'm not gonna really focus on that. But as you can see, what changed is the source and destination MAC. But because we are using NAT, our source IP should change as well. So I'm gonna look at the IP header. Yeah. So before hitting the router, the source is 10.0.0.1, destination 88. After hitting the router is 192.168.122.85, because there is a NAT happening on gig 10. But if I were to, on PC 1, cancel this ping and continue this. No, not here. Continue here. I'll close this again. Close it. If I PC1, I ping PC2. PC2. Oh, there it is. If I ping PC2 and capture R1 again, start Wireshark, there should be.
You should ping it again.
Okay. Let's flood it.
Maybe
Damn
it should stop
GNS3.
the Wireshark.
For me. Yeah. As you can see, the source and destination here do not change. But the thing is, if I take this packet, which is the source is 10.0.1.2 and 2.2.2, if you look at the layer 2 headers, right, the source is the router, not our PC1. That's because the traffic is routed through the router. If I click on this one, again, the source here is our PC2. And the destination is .1 over there. See? Right now, and again, the source is the router, destination is PC1. The reason you can see conflicting source and destination is because on this interface there is a there's two different sub interfaces of a router responding to the same trunk. So there's some ping replies are different than the other ones, but the one we're looking at for is this one. The source is the router and the destination is PC. The source is the router and destination is PC. But the source IP and destination IP does not change if there is no NAT over a layer 3 segment. I think that's all for the packet captures to show.
So yeah, I don't have any question, but if you want to add more things about layer 2, I don't have any points to add. Like you can add more if you like.
But one thing I think we missed was that we didn't talk about the troubleshooting for PC3 and PC4.
Okay.
So just gonna cancel this, right? If I open PC3 and if the trunk is configured correctly, since PC3 is on DHCP as on VLAN 1, it should receive a DHCP address. But it can't. It cannot find a DHCP address. So troubleshooting on a layer 2 scale here from PC3 to the router, there's three things to be considered. First, since PC3 is the one receiving a DHCP address, I cannot confirm anything on PC3. Then I can, one troubleshooting step I can do is to give PC3 a fictional IP address. An IP address is just set, just to test connectivity. 10.0.1.3.255.255.255.0 10.0.0 1.254. And then let's try to ping our gateway. It should not work. Right? Yes, it does not work. The host is not reachable. We can trace it, see where it fails. It cannot resolve to anything because tracing without a layer. So if we trace it and nothing shows up, it's a layer 2 issue. Because trace is a layer 3 troubleshooting method. But yeah, so something is wrong with our layer 2 access here. We know the connection from switch 1 to R1 works correctly because our PC1 and PC2 can receive and contact the internet, no problem. So something is wrong with our port channel. Then we gotta look at our port channel configuration and see if anything is wrong. I go to switch 1 here, and I should open switch 2. Assuming if you didn't see the logs already. Well, let's look at our do show run section port channel. Nothing. Show run. As you can see, let's first of all verify if our port channel is up. What's going on? But damn switch. It's putting queues on itself. There it is. Show port channel. Sorry. Show channel group channel. Was it channel group? So link. If I do show IP interface brief, I should see the channel, if anything. And you can see it's up and up. But with port channel, that's not the only thing we should do to confirm its functionality. You should also look at this, the LAC. At this point, I'm using LACP, but you should look at the LACP stats for the port channel as well. So I think we'll show LACP. I found it. We'll show LACP 1 and neighbor. You can see our gig port. You can see our ports. They're both in the working state for switch 1. And since the good thing with using a port channel protocol is if it's working on one side, it's working on the other side. Otherwise, you wouldn't know. So it's not a port channel. So it might be the configuration on the trunk. So that's what I'm gonna verify. Show running config interface port channel. One. So interface switch port trunk encapsulation.trunk switch port mode trunk. So far, so good. Let's check the trunk on the other side. Show run interface port channel 1. Switch port trunk encapsulation.trunk switch port mode trunk. We can see it's a native VLAN mismatch. So you might ask, okay, there is no native VLAN configured here, but it is. Native VLAN by default is VLAN 1. But on switch 2, native VLAN is VLAN 2. On Cisco devices, if you do this, the STP will detect it and it will put the link down. Like it will not let any traffic go over it. But if STP wasn't there, you could technically ping from PC1 to PC2 sorry, you can technically ping from PC1 to PC4 without any issues. To confirm that, let's open PC4. Show IP. There's no IP. IP 10.0. I'm gonna give it 1.4, 2.5, 2.5, 2.5, 0, 10.0, 1.2.4. PC1. So if this wasn't the Cisco switch, let's see, 10.0, 1.4. Yeah, it doesn't. But if this wasn't the Cisco switch, we done an STP on it, it would have pinged. This is a concept called VLAN hopping. So the way it works is native VLAN 1 is configured on switch 1, native VLAN 2 is configured on switch 2, and PC1 sends the packet out, right? Since it's part of VLAN 1, the trunk protocol will not tag it because it's a native VLAN. So the untagged traffic will get into switch 2. Switch 2 is configured with native VLAN 2. So it will forward the untagged traffic into the VLAN 2. And therefore PC1 can contact PC4. But Cisco switches have put up a security measure that doesn't let it happen. So the fix basically is to go to switch 2, interface port channel 1, and switch mode truck native VLAN. I'm going to put 99. First, you have to create. Because always remember, the best practice is to put the native VLAN on something you're not using. So, come on. See, because there is a native VLAN mismatch, you can see the spanning tree blocking the port channel 1 on VLAN 99. That's why the ping doesn't go there. If not for this STP, we would. So let's go to switch 1 on P interface port channel interface port channel 1, switch mode truck native VLAN 99. Exit. And now PC3 should technically be able to ping the default gateway. I'm just going to test if it can ping PC1 first, though. Technically, yeah, port is restored. So ping it. Why? It pings the default gateway, but it doesn't ping PC1. PC1, where are you? They are. Oh, this 1.2, that's why. So now PC1 can ping PC3. And if I do IPDHCP, Dora, there it goes. Same with PC4, it's fixed also. IPDHCP. Dora.
There.
And now PC4 can ping the internet as well. There it is.
Awesome.
The network is fully operational at this point. think we covered almost everything, as I remember.
Okay,
No.
so thank you so much for this useful information, Michael. I hope this information been informative for the student, and thank you for being with us.
Oh, it's a pleasure. Thank you. Thank you very much for listening.
All right. See you guys. Bye.
Yep. Bye.